So in the last video, we started talking about convergence in RD, and we extended a whole lot of our definitions from the real line to the whole d-dimensional Euclidean space. I think that was sort of obviously a useful thing to do, right? We like talking about convergence in larger spaces, and actually we could do that relatively easily. A lot of the definitions and even a lot of the proofs extended almost immediately once we chose good definitions. This video, unfortunately, is probably not going to feel so good, at least the first time you read it. We're going to be doing an introduction to topology, and really what that means is we're going to be looking at a lot of our old results and writing them in a new language which probably isn't going to feel quite as natural at the beginning. It's going to take a little while for this to sink in, but I'll give you sort of a hint as to the first place that this is going to feel useful. If you look at most of our proofs so far, we have a lot of boilerplate at the beginning of the proofs. We often say things like, fix an epsilon greater than 0, then there exists an n such that, and so on and so forth. And then a lot of the proofs also have sort of a similar feeling, where we're using the triangle inequality sort of all over the place and getting lots of explicit estimates of the distance between different points. One thing that's going to show up as we start getting used to using these definitions from topology is that we'll have proofs which don't have so many triangle inequalities, which don't have so many explicit calculations. We're going to be able to replace these explicit calculations with sort of arguments which people call soft arguments. That is, ones where you don't actually have to estimate distances. Okay, so that's going to take a little while, and unfortunately you'll just have to bear with us as we set up the notions in topology. So the first most important definition is for an open ball and an open set. So the open ball, which I'll denote B of x comma r, is a collection of all points y, so that the distance between x and y is strictly less than r, right? So it's what you expect, right? In D2, D equals 2, this is just a circle and everything inside of the circle, but not the boundary itself. Okay, so it's really important that we have a strict inequality there. Okay, so that's what's called an open ball. We have another definition, the complement, and the complement of a set A is just everything that's not in A. And then finally, we have a general definition for an open set. We call a set A open if for every element x of A, there exists some r greater than 0, so that the ball around x of radius r is contained in A. So what does that look like? Well, we have this set A, which I've drawn with this outline, and we have this little point here, and we have to be able to draw some tiny ball which goes around that point and doesn't ever leave A. All right, so one thing which I'm not going to prove right now, but which is true, and which you can check for yourself without too much difficulty, is that the open ball is indeed an open set. Otherwise, we'd be a little bit unhappy. One thing that you can probably guess from the picture that I just drew, and the fact that I put so much emphasis on the fact that the open ball has a strict inequality, is that if I draw a set along these lines, and this line that I use to draw the outline of my set is contained in the set itself, that set isn't going to be open. And why is that true? Well, right, you can choose a point x which is exactly along this boundary, and it's sort of clear from the picture that if I draw a circle around that point, no matter how tiny the circle is, it's always going to catch the points that are outside of A. Okay, so whenever I'm talking about an open set, I'm often going to be drawing these sorts of squiggly sets for proofs, but if the set is supposed to be open, the boundary, that part that I actually draw, is never going to be sitting inside of A. We'll revisit that later on when we start actually doing some calculations. So what are some sets that are open? So first of all, the thing that we call the open interval from 0 to 1, that's open. How do you prove something like that? Well, fix some x in 0, 1, and define r to be half of the minimum of the distance from x to 0 and the distance from x to 1. So what does that look like? Well, I have some point which is an interval x, and my radius r is going to go halfway to the closest boundary point. So in this case, that one looked closer in the picture, and I just draw this little ball here. Okay. So hopefully that's sort of okay. And at this point, we're very used to the fact that the order in which we choose things is important in definitions. So if I look at the definition of an open set, right, I have the for all x first, there exists an r second. So when I'm proving something is open, I ask you for an x, and then I have to give you an r. And r in general is going to depend on x, right? Otherwise, it would be hopeless. Similarly, the closed set 0, 1, oops, I said it's closed, but what I really wanted to say here is not open. And what's the proof? Well, I just have to find a bad point. So I consider x is equal to 0, and it's sort of clear, right, that the interval x minus r, x plus r is not contained in the closed interval 0, 1 for any r greater than 0, right? If I look at that interval here, I'm always going to be containing some point that's strictly negative. So that's pretty quick. And then, of course, like I said, the open ball around x of radius r is always open in any dimension. So I'm not going to prove that, although there's a proof in the lecture notes if you would like to look. We have a similar definition for closed. We say that a set A is closed if the complement, A complement, is open. All right. At this point, I'm going to take a break from the definitions and start talking about something that's an issue for many people when they start working with closed and open sets. And the issue is that we have a lot of intuition from the real line, and this is one of those situations where that intuition can steer us very far astray. And the issue is that over the real lines, most sets that we actually bother writing down are open or closed or half open. And even sets that we don't write down explicitly like that, ones that we just sort of draw, right, are generally going to be unions of intervals. Those are the things that we write down most easily. And so they're unions of things that are open or closed or half open. Right? And so we sort of get used to thinking of this idea that being open or closed is sort of a standard thing or common thing. But that's not true in R, and it's really not true in RD. Most sets are sort of weird looking. So here I'm drawing two sets here, and I'm using blue, like here, to denote the sort of closed boundary, that is, these points which are in blue are parts of the sets, and green here to denote the open part of the boundary, so these points here denote the sort of outline of the set, but they're not actually sitting in the set. And you can see, right, there's sort of chunks of this which are closed and chunks of this which are open, and it's not half open, right? There's some part of it that looks open, some part of it that looks closed. And it's just sort of this weird thing. And here we have sort of more little chunks of the boundary, and there's sort of an internal boundary, right? There are all sorts of weird things that can happen in sets, and sets just don't look open. They don't look closed. The complements aren't open. The complements aren't closed, right? There's just sort of nothing nice about most sets. So if you want to talk about a set being open in RD, it's really only going to be open if you've built it to be open, or you can for some reason assume that it's open, usually because of information given in the theorem that you're trying to prove. Okay, so things are open only for special reasons. If you have a generic set, it's just not ever going to be open. All right, so where do open and closed sets come from? Well, the most important thing to say is that you can build open and closed sets from other open and closed sets. So there are a couple of sort of base cases for open sets. So the empty set is open, the whole Euclidean space RD is open, and these open balls are open. So we know a few examples. And then we can build up more open sets by taking unions and intersections. So if I have any collection of open sets, the proofs of the first two parts of that theorem I'll leave as exercises. I think they're not terribly difficult. The third part requires a little bit more care. So I want to prove that if I have a finite collection of open sets, the intersection is also open. So how do I prove that? Well, I'm just going to go straight to the definition. So I'm going to fix some point x, which is in the intersection of all of these open sets. So in particular, that means that for every index I in the big collection capital I, x is contained in ui, and of course ui is open. And that means that there exists some r, depending on I and x, so that the ball of radius ri around x is contained in ui. That's what it means for ui to be open and to contain x. So now I take r to be the minimum of all of those. And since I is a finite set, that little r is itself finite and strictly positive. And then b of xr is contained in the intersection of b of x Ri, which itself is contained in the intersection of the ui's. Okay, so that's a fairly short argument. And one thing that you'll notice if you look at the theorem up here, right? We had two parts of the theorem that look very similar, right? If I have a collection of open sets, the union is open or the intersection is open, but we needed this extra assumption when we were talking about intersections. And you can immediately see where that intersection shows up in the proof. Here, I took this radius r to be the minimum of the radii that showed up for all of the individual sets. Now, if my index set I is finite, the minimum of a finite collection of strictly positive numbers is itself strictly positive. But of course, if my index set I were infinite, then the minimum of a bunch of infinite then the minimum of an infinite collection of strictly positive numbers could itself be 0, at which point this part of the argument would fall through. So that's sort of what goes wrong with the proof, and it's not terribly difficult to construct a bad example based on that observation. So consider, for example, the collection of open sets un being the interval from -1 over n to 1 over n. So obviously those are all open sets, but the intersection of all of those open sets is just a single point, 0, and we can see that 0 is definitely not an open set, right? There's no way that there's a ball of any radius that's strictly positive around 0, which is entirely contained in just the single point 0, right? Individual points are certainly never going to be open. There are some very similar results for closed sets, and I'm not going to prove these because more or less they follow from the results for the open sets or from sort of similar arguments. So the empty set is closed, and the complete Euclidean space Rd is closed, so they're both open and closed. These balls here, which are almost identical to the open balls, except that I have a less than or equal sign there, those are all also closed, and actually that's still true if I just look at R greater than or equal to 0. Okay. So those are sort of the baseline closed sets that are easy to write down. Then I have two parts of the theorem that are very, very similar. If I have a collection of closed sets, then the union is closed as long as the index set I is finite. And if ui is closed, then the intersection is always closed. So this is sort of the same thing as for open sets, except the extra condition got flipped. For open sets, I need the index set to be finite for intersections, and for closed set, I need the index set to be finite for unions. Okay. So what are we actually going to be doing with open and closed sets? So one thing that's nice about them is that they turn out to be sort of a nice way to talk about limits. So here's an important theorem. A set A is closed if and only if every convergent sequence contained in A has a limit that is also in A. Okay, so that's what it means to be closed. Every convergent sequence has a limit that's in L, and that's in A. Before going to prove this, I want to think for a second, what can go wrong here? That is, how can a set A fail to have this second property here, that every convergent sequence contained in the set has a limit that's also in the set? Well, the basic problem is that you can have a sort of a missing boundary point. So for example, if A is the interval from 0 to 1, but not containing 0 or 1, then the sequence an is equal to 1 over n is certainly all contained in A, and we certainly know the limit is 0, but 0 is not in A. And it turns out that's sort of the only thing that can go seriously wrong, and that's going to guide our proof. So let's go through the details. First, we're going to go sort of the forward direction. We're going to have a set A that's closed, and we're going to prove that every convergent subsequence has a limit that's also in A. And our proof is going to be by contradiction. So let's assume that there exists a sequence contained in A whose limit L is not sitting in A. So what does that look like? Well, it looks sort of like this. And notice I've drawn L a little bit away from the boundary of A. And that's because A is closed, so we know there's this little ball around L that's entirely contained in A complement, right? So that's actually sort of a good picture. That little point there really does have to be separated away from A. And here I've drawn my little convergent sequence. And if you look at the picture, you can already see what's going wrong, right? I have this convergent sequence which is supposed to be going towards L, but L has this ball, this sort of shield around it, which none of the elements of that sequence is allowed to be in. And so that's obviously going to be a bit of an issue if that sequence is supposed to be converging to L. So let's turn that into something that looks more like math notation. So here's how we do it. So we have a sequence an converging to a limit A. We know that A complement is open. So there exists some r greater than 0, so that the ball of radius r around the point L is contained entirely in A complement. So that's exactly what I've drawn here. Now fix epsilon equal r over 2. Then for all n, we know that an is not contained in the ball of radius r around L. And so in particular, that means an minus L, the norm, is bigger than or equal to r, which is strictly bigger than epsilon. Okay? So we have an epsilon for which we don't have this distance getting smaller than epsilon for n large. And so that exactly means that an does not converge to L, which is a contradiction for the original assumption. So that's the first direction. In the reverse direction, we're going to go by contradiction again. So that is, we're going to assume we're going to have a sequence, we're going to have a set A that satisfies the property. Every convergent sequence has a limit belonging to A, and we want to prove it's closed. And the way we're going to do that is we're going to assume that A is not closed. So what does that mean? Well, the only thing that it means for set A not to be closed is that A complement is not open. So what does that mean? That means that there exists some point x in A complement, so that for all r greater than 0, the ball of radius r around x has some intersection with A. So all of this is sort of boilerplate, right? I'm just expanding the definition. And it's clear that this is sort of what I have to do, right? There's no other thing that I can do at the beginning of the proof because I need to actually use my assumption. And at this point, I have to think a little bit, all right, what am I going to be doing? And I like to draw a little cartoon. What does that mean? It means I have a set A that looks sort of like this, like a half open set, for example. And I have this point X that has this property. Whenever I draw a ball around X, I hit part of A. Well, that just means that X has to really be right on this little boundary point there. And that's going to give us a good idea of what we should do next, right? What are we going to do? We're going to fix some sequence Rn, and I'm going to say Rn is equal to 1 over n, although it doesn't really matter that much. And we're going to let Xn be a sequence of points which are contained in the ball of radius Rn around X and also A. Why can I do that? Well, I can do that because I know that for every R, the ball of radius r around x intersect A is not empty. And so in particular, the ball of radius Rn around x containing, the ball of radius Rn around x has some intersection with A. And so I just choose some point which is in there. Okay, so I have this sequence, xn's, and they're getting closer and closer to x. And in particular, for any fixed epsilon greater than 0, for all n bigger than the ceiling function of epsilon inverse, the norm of xn minus x is less than epsilon. Well, that's just what this means, right? And therefore, xn converges to x because I've just checked this convergence condition, but x is not an A by construction, and so I have a contradiction. Okay, so this proof is sort of almost on autopilot when we go backwards. Going in the first direction, maybe we had to think a tiny bit more. All right. So far I've talked about open sets and closed sets, but there are quite a few other definitions which sort of go along with those definitions. They're less important, but they're sort of useful shorthands when we're doing proofs with open sets. And so I'm just going to list all of them here and give little cartoons. We have interior points, isolated points, accumulation points, and boundary points. And all of these are for a fixed set A. So here's a definition. A point X is in A is an interior point if there exists some r greater than 0 so that the ball of radius r around x is contained in A. So what does that look like? If I have this sort of blobby A up here and I have a point x here, it means that I can draw this little circle around x, and the circle is going to be staying inside of A. So you'll notice this is almost what's going on for the definition of an open set, except here we're sort of saying, well, from the point of view of this one point x, it looks like A is open. And so it's not terribly difficult to check, and you can do this as a little exercise, that a set A is open if and only if every point is an interior point, right? That's really just the definition of an open set. A point is an isolated point if there exists some radius r greater than 0, so that the ball of radius r around x intersect A is just x. So here's a cartoon of an isolated point, and here's my isolated point over here, and so I can draw this little ball, which contains only one point in my set A. Okay, so hopefully so far so clear. The next two definitions maybe take a little bit more thought because there are a few different pictures that can go along with them. So we say a set is an accumulation point if for every radius r greater than 0, the ball of radius r around x intersect A contains infinitely many points. But we don't require that x itself be sitting inside of A. So what are the types of things that can happen? Well, one option, of course, is if you're just sitting in the middle of a set A, like that, and the ball contains points. Well, okay, of course, you're going to be an accumulation point, right? So here, definitely you're an accumulation point. That's sort of the easy version. And then the version where you have to think for a second is maybe you have a set like this, the half open interval from 0 to 1, and I choose a point that's just here on sort of the right-hand boundary. So it's not contained in the set, but it's right next to the set. And you can see for yourself, if you draw any little ball there, it's going to contain many points in the set A. So there are sort of two ways to be an accumulation point. One option is that you're sort of inside, like in picture A, and the other is that you're sort of on this boundary-looking region, like in picture C. Okay. The last definition is sort of similar. We say that a point is a boundary point if, for all radius r greater than 0, the open ball of radius r around x contains at least one point of A and also one point of A complement. So the easiest way to be a boundary point is something like B, right? So here we have this isolated point, and it's obviously a boundary point, right? We can look at this little ball of small radius, and it contains, well, the point in the middle, so that's one point of A, and of course nothing else in the ball is an A. So here we definitely have a boundary point. And the other thing that can happen is, well, we can have the same cartoon that we had in C with the half-open line. This point here, which I've been sort of referring to as a boundary because it looks like a boundary, is also a boundary point in this technical definition. Okay, so that's a lot of definitions to take in fairly quickly. These definitions aren't quite as important as the definitions for open and closed sets, but I will be using them fairly frequently, and so you should get used to them, as quickly as you can. I think the names are rather good, so hopefully they'll help us remember what's going on. Just to try to get them sort of locked into our head, we'll do a couple of examples very quickly. So if I look at the open interval from A to B, every point is an interior point. No point is isolated, right? That's sort of clear. The set of accumulation points, well, this is a little bit less clear, but the set of accumulation points is certainly everything that's inside here is an accumulation point. And then as I just saw in my cartoon, these boundary points are also accumulation points. And then these boundaries themselves, A and B, those are the only boundary points. For the closed interval AB, almost the same thing happens. What are the interior points? The interior points are just the open set from A to B. No points are isolated again. Every point is an accumulation point, and again, these points on the boundary in the picture are the only boundary points according to our technical definition. So almost the same thing. And you'll see actually, if you look at these, that even though we're talking about an open interval here and a closed interval here, we get exactly the same answer for all of these definitions. So that's not an accident, right? Somehow when you're looking at these definitions of interior isolated accumulation and boundary points, we're somehow ignoring a little bit what's going on right at the boundary because they don't really matter for all of these definitions. Now we look at a couple of more complicated examples. Maybe I'll do the natural numbers first. No point is an interior point, right? Because all of the points are sort of isolated. Every point of n is an isolated point. No point of n is an accumulation point, and every point of n is a boundary point. Okay, so that one's sort of easy to check because all of the points are obviously very far separated. Q is, of course, fairly complicated, and unlike the other parts, unlike the other examples that I've just done, you can't really sort of check all of these things very, very quickly. We've checked most of them before using other language. So no point is an interior point. What does that mean? Well, I take a point in Q, and what does it mean to be an interior point? Well, I need to have a little ball around that point that's entirely contained in my set. And we know that if you take any ball around any point in the real line, it's going to contain some points that are not in the Q. No point is an isolated point. Well, the same thing. This isn't actually very trivial, but quite a long time ago we proved that Q is dense in R, and that exactly means that no point is isolated. Every point is an accumulation point. Well, we didn't prove that, but it's sort of straightforward to check, right? And every point is a boundary point, again, fairly straightforward to check. Okay. Let's do an example, sort of tying together a couple of these ideas. So we have this this closed set from 0 to 1, and we might want to know, can we write that as an intersection of open sets or as a union of open sets? The answer, well, I'm going to ask that you pause the video for a second and try to do this yourself, and I'll of course just carry on assuming that you've paused and given it a shot. The answers to these two questions, even though the questions themselves look very similar, are going to feel sort of different. So if we want to write this as an intersection of open sets, the obvious thing to do is actually just try to write it down. And so here's what I'm going to do. I'm going to let ui be equal to minus 1 over n, 1 plus 1 over n. And it's not terribly difficult to check that the intersection of these sets is exactly the interval from 0 to 1. I'm not going to prove that, but the proof is fairly short, right? It's clear that the closed interval from 0, 1 is contained in all of these, so it's at least that big. And in the other direction, if I take any point that's a little bit outside of this interval, of course, it's eventually going to get cut off by these 1 over n's. So that's sort of part 1. Part 2, though, we're not going to give an example, because I claim that, in fact, you can't write 0, 1 as a union of open sets. And I'm going to give sort of an indirect proof, which is maybe a sort of a first peek at the power of some of these notions. Recall, if a set A can be written as the union of open sets, then A is itself open. We know that this isn't an open set. Therefore, it's not possible that you can write it as a union of open sets, because otherwise the theorem would kick in. So we have sort of an indirect proof by contradiction that there's no way to write the closed interval 0, 1 as a union of open sets, but it's fairly easy to write it as an intersection of open sets. All right,